Hey math fans! Welcome to Math Olympiad Academy, your trusted space for advanced problem solving and logical reasoning. We sincerely thank our subscribers and all viewers for your continued support. In Lesson 27, we present a rigorous, step-by-step solution to scary-looking limit, and limit easy with a step-by-step approach. In this problem, evaluate the limit as n tends to positive infinity of the integral from 0 to 1 of the sum from k equals 1 to n of 1 over the quantity nx squared plus kx plus n with respect to x. Lesson objective. In this lesson, students will identify a Riemann sum hidden in a sum integral expression, justify the interchange of limit and integral using domination, evaluate the resulting double integral via iterated integration and known logarithmic identities. Before we begin solving, many students have asked me, where should we start with this problem? In this first step, we begin by re-expressing the denominator. Since n is strictly greater than 0, we can factor n out of all terms in the denominator. This gives n times the quantity x squared plus 1 plus k over n times x. Therefore, each term in the sum becomes 1 over n multiplied by 1 over the quantity x squared plus 1 plus k over n times x. Hence, this step reveals the structure of a Riemann sum, which we now make explicit in step 2. Now, look at the entire sum, the sum from k equals 1 to n of 1 over n, multiplied by 1 over the quantity x squared plus 1 plus k over n times x. Let t equal k over n. Then, the sum becomes the sum from k equals 1 to n of 1 over n times 1 over the quantity x squared plus 1 plus t times x. For each fixed x in the interval from 0 to 1, this is a Riemann sum for the function f sub x of t, defined as 1 over the quantity x squared plus 1 plus t times x, where t plays the role of k over n, and k takes the values 1, 2, 3, up to n. Thus, the sum can be written as the sum from k equals 1 to n of 1 over n times f sub x of k over n. Therefore, for each fixed x, as n grows large, this sum approaches the integral from t equals 0 to t equals 1 of 1 over the quantity x squared plus 1 plus t times x with respect to t. At this step, we aim to bring the limit inside the integral. To do this rigorously, we apply the dominated convergence theorem. First, observe that for all x in the interval from 0 to 1, and for every k from 1 to n, the quantity nx squared plus kx plus n is greater than n. Therefore, each term in the sum is less than 1 over n. Since there are n such terms, the entire sum is less than n times 1 over n, which equals 1. Thus, the whole expression is bounded above by the constant function g of x equals 1, and this function is integrable on the interval from 0 to 1. Hence, by the dominated convergence theorem, we are fully justified in interchanging the limit and the integral. Therefore, we may interchange the limit and the integral. That is, the limit as n tends to positive infinity of the integral from 0 to 1 of the sum from k equals 1 to n of 1 over the quantity nx squared plus kx plus n with respect to x equals the integral from 0 to 1 of the limit as n tends to positive infinity of the sum from k equals 1 to n of 1 over the quantity nx squared plus kx plus n with respect to x. But from step 2, we know that for each fixed x, this limit equals the integral from t equals 0 to 1 of 1 over the quantity x squared plus 1 plus t times x with respect to t. Hence, the entire expression becomes the integral from x equals 0 to 1 of the integral from t equals 0 to 1 of 1 over the quantity x squared plus 1 plus t times x with respect to t, then with respect to x. So, by the dominated convergence theorem, we bring the limit inside the integral. Then, recognizing the inner sum as a Riemann sum, we replace it with an integral in the variable t. In this inner integral, x is treated as a fixed constant, and we integrate only with respect to the variable t. This yields a double integral, namely, the quantity L equals the integral from x equals 0 to 1 of the inner integral from t equals 0 to 1 of 1 over the quantity t times x plus x squared plus 1 with respect to t, then with respect to x. In other words, the inner integral is explicitly the integral from t equals 0 to 1 of 1 over the quantity t times x plus x squared plus 1 with respect to t. Now, let us evaluate this inner integral in step 5. One more time, we recall treat x as a parameter, that is, as a constant for this stage, and consider t as the variable of integration. As a reminder, the integral of 1 over a times t plus b with respect to t is equal to 1 over a times the natural logarithm of a times t plus b plus a real constant. We apply this formula to our inner integral. So, the integral from t equals 0 to 1 of 1 over the quantity t times x plus x squared plus 1 with respect to t equals 1 over x times the natural logarithm of t times x plus x squared plus 1 evaluated from t equals 0 to t equals 1. Then, using the properties of the logarithm, the inner integral evaluates to 1 over x times the natural logarithm of the quotient x squared plus x plus 1 divided by x squared plus 1. Let h of x equal 1 over x times the natural logarithm of the quotient x squared plus x plus 1 divided by x squared plus 1. Since we will integrate this function h of x from 0 to 1, we must verify that it is integrable on this interval. The expression involves division by x, so we examine the point x equals 0 separately. When x equals 0, the original inner integrand becomes 1 over t times 0 plus 0 squared plus 1 equals 1 over 1, which is 1. Therefore, the inner integral is the integral from t equals 0 to 1 of 1 dt, which equals 1. Now consider the limit of h of x as x approaches 0 from the right. We can write the logarithm as natural logarithm of 1 plus x over x squared plus 1. Using the approximation, the natural logarithm of 1 plus u is approximately equal to u when u is near 0. We find that h of x behaves like 1 over x times x over 1, which is 1. Thus, the limit as x tends to 0 from the right of h of x is 1. This means h of x has a removable discontinuity at x equals 0, and the function extends continuously to x equals 0 by defining its value there as 1. Therefore, for all x in the interval from 0 to 1, the inner integral equals h of x when x is greater than 0, and equals 1 when x equals 0. In other words, the value of the inner integral at x equals 0 is defined by continuity. And since changing a function at a single point does not affect the value of its integral, we may write L as the integral from x equals 0 to 1 of 1 over x times the natural logarithm of the quotient, x squared plus x plus 1, divided by x squared plus 1 with respect to x. Now, our aim is to evaluate the integral, denoted L, which is the integral from x equals 0 to 1 of 1 over x times the natural logarithm of the quotient, x squared plus x plus 1, divided by x squared plus 1 with respect to x. To proceed, we first apply the properties of the logarithm. The logarithm of a quotient equals the difference of the logarithms. Thus, we rewrite L as the integral from x equals 0 to 1 of the quantity natural logarithm of x squared plus x plus 1 minus natural logarithm of x squared plus 1 all over x with respect to x. Next, by linearity of the integral, we split this into the difference of two integrals. L equals L sub 1 minus L sub 2, where L sub 1 is the integral from x equals 0 to 1 of natural logarithm of x squared plus x plus 1 over x with respect to x. And L sub 2 is the integral from x equals 0 to 1 of natural logarithm of x squared plus 1 over x with respect to x. Now, in this seventh step, we aim to evaluate the final integral denoted L, since L is now the difference of L sub 1 and L sub 2. And since inside these integrals, we face a quadratic expression inside the logarithm. Let us begin by using algebraic identities to simplify this logarithm of x squared plus x plus 1. Since 1 minus x power 3 equals x squared plus x plus 1 times 1 minus x. For x different from 1, x squared plus x plus 1 equals 1 minus x power 3 over 1 minus x. Taking logarithms on both sides, we obtain natural logarithm of x squared plus x plus 1 equals natural logarithm of 1 minus x power 3 minus natural logarithm of 1 minus x. So after integrating term by term, this yields the integral L sub 1 equals the integral from 0 to 1 of natural logarithm of 1 minus x power 3 all over x dx minus the integral from 0 to 1 of natural logarithm of 1 minus x all over x dx. Here, in this stage, we recall the following standard result, the integral from 0 to 1 of natural logarithm of 1 minus x power alpha all over x dx equals minus pi squared over 6 alpha, for alpha strictly greater than 0. Apply this standard result, we obtain. For alpha equals 3, the integral from 0 to 1 of natural logarithm of 1 minus x power 3 all over x dx equals minus pi squared over 6 times 3, which equals minus pi squared over 18. Likewise, for alpha equals 1, the integral from 0 to 1 of natural logarithm of 1 minus x all over x dx equals minus pi squared over 6 times 1, which equals minus pi squared over 6. This yields the integral L sub 1 equals minus pi squared over 18 minus pi squared over 6, which equals pi squared over 9. Regarding the integral L sub 2, to evaluate it, we will apply the power series method. For this objective, we recall this standard result. For all r less than 1, the natural logarithm of 1 plus r squared equals sum from m equals 1 to infinity of minus 1 power m plus 1 all over m times the quantity r power 2 m. So, since x squared plus 1 equals 1 plus x squared, the natural logarithm of 1 plus x squared equals sum from m equals 1 to infinity of minus 1 power m plus 1 all over m times the quantity x power 2 times m, where x is less than 1. So, the integral L sub 2 becomes equal to the integral from 0 to 1 of 1 over x times sum from m equals 1 to infinity of minus 1 power m plus 1 all over m times the quantity x power 2 times m dx. This yields L sub 2 equals sum from m equals 1 to infinity of minus 1 power m plus 1 all over m times the integral from 0 to 1 of the quantity x power 2 times m minus 1 dx. Since the integral of x power 2 times m minus 1 has the antiderivative x power 2 times m over the quantity 2 times m from 0 to 1, which is 1 over 2 times m. By replacing this value in the integral L sub 2 and moving 1 over 2 outside the sum, we obtain L sub 2 equals 1 over 2 times sum from m equals 1 to infinity of minus 1 power m plus 1 all over m squared. So, we can also express this integral L sub 2 as 1 over 2 times s sub m, where s sub m denotes sum from m equals 1 to infinity of minus 1 power m plus 1 all over m squared, which shows obviously the alternating series nature of the expression s sub m, whose sum is known to be pi squared over 12. Hence, the integral L sub 2 equals 1 over 2 times pi squared over 12, which is pi squared over 24. Thus, by combining our previous results, we obtain L equals L sub 1 minus L sub 2 equals pi squared over 9 minus pi squared over 24 equals pi squared times 1 over 9 minus 1 over 24. On the other hand, the least common multiple of 9 and 24 equals 72, which lets us write L equals pi squared times 8 over 72 minus 3 over 72, which is 5 times pi squared all over 72. Conclusion: the limit as n tends to positive infinity of the integral from 0 to 1 of the sum from k equals 1 to n of 1 over the quantity nx squared plus kx plus n with respect to x is evaluated to be 5 times pi squared all over 72. I hope you enjoyed this step-by-step solution. Keep practicing, share this lesson with your friends, and don't forget to subscribe to Math Olympiad Academy for more exciting math challenges. See you in the next lesson!